Hi everyone, good morning. Welcome back to this channel, Fidit Technologies, with me Dito. In today's video, we are going to continue the previous video on the mesoscale modeling of composite laminate in Abaqus. In the previous video, we used cohesive elements to connect one ply to another, while in the current video that we are recording now, we are going to model the connection between plies using cohesive surface behavior. So instead of using elements, we're going to use a contact interaction that has cohesive behavior. So we need to set them in Abaqus under the module interactions. Okay. So what we are going to do is the same as in the previous model. So in the previous model, we have one ply, and then we make some partition, right, if you remember, and then we make another partition for the cohesive elements, and then we assign a cohesive element here, and then this is the ply. But in today's video, what we are going to do is basically we will make four plies. All right, well, this is the 0, this is the 90, 90, 0, and then we will assign a cohesive interaction between these two uh, faces from two different plies. All right, so what I'm gonna do, I'm gonna start with the previous model. I will just copy the model, uh, cohesive surface. Okay, we're going to use, so I'm gonna work with the new model. With this one is using cohesive element, this one is using cohesive surface, but then now I'm going to modify the part, because now we need to remove several of them, or maybe I will just remove everything, just to make it clear for you guys so you can repeat what I'm doing. So create part. uh, Oops, I still have another part. Let me delete this part. Yes, so let's create it. So it's starting from part 1 right now. It's a modeling space, 3D type, deformable. Now the shape is solid. I'm going to use extrusion. Click and then click here, create rectangle, create lines, rectangle lines, 0 comma 0, and then 2. To make the simulation faster, this time I don't want to use the full length of 200. I'm just going to use 100 times 25 to make it the simulation faster. Okay, and then I click here, click done, and then the depth. In the previous video, because we want to model the whole laminate, the depth was 1 millimeter, right? Because one elementary ply thickness was 0.25, and then we have 4 plies, so the total thickness will be 1 millimeter. Now in this modeling, we need to model each ply, so we're going to use 0.25 depth millimeter. Okay, so this is like one ply. All right, so what I'm gonna do now is that I'm going to make another ply. I'm going to just copy this part, copy part uh, 1, but this one I want to make it a 90 degree. Okay, so I have a two part now. First is the part number 1, which will represent a 0 ply, and I'm going to have a part 1 but oriented in the 90-degree directions that I will assign later in the property. Now I already have the materials. I only need material number 1 right now, because I will not use the material number 2. The material number 2 is for the cohesive elements. Now we don't need this, so it's okay. I can delete it if I want. Yeah, let's delete it. If you don't have it, you don't need to delete anything. The same thing here, the cohesive, you don't need to delete actually, but if you want, you can delete. If you don't have, no need to worry. Now we need to assign this guy. assign section. I will assign this guy this using section 1 material 1, correct? And the same thing for the 90 also. I'm using the same thing, section 1 material 1. The only difference is the next step. For the part 1, I will click here, assign material orientations, and then I click done here after I choose the default orientation. So I'm going to use coordinate system. The axis is 3, and then I will say it's a 0 rotations. All right. And then for the 90, I will assign this guy, select all of this, how you call it, cell, and then use here, click here, and then coordinate system, axis number 3. The angle will be rotated 90 degree. So now it becomes a 90-degree ply. Okay. And then we will assemble them. Oh, I already have assembled from the previous one. Let's delete this one first. Delete feature. I shouldn't use this one. And then okay, and then let's create instance using part 1, and don't forget to create auto offset here. So you need part 1 1, part 1 2, you have 90, you have 90 again, you have part 1. Okay, then don't click OK. If you click OK, maybe OK is okay. Okay, because you haven't clicked. If you click here again and then you click OK, uh it will, how to say, will create another one, but you don't want. Just click cancel. You already have 4 now. Okay, so what we are going to do, uh just leave it like this. You can directly, how to say, translate all of this guy to here to stack them, but then we will have difficulties later to choose this surface and this surface. So if everything already well stacked in this assembly right now, we will have a difficulty later on when choosing the master and slave during these contact interactions. So it's better to leave like this, and then we will come back to assembly again to make sure they're nicely positioned. Okay, step. So now let's create step. I think we already have the step, so we don't care. Interactions. Now this is what I said, that is the most important one. So we are going to stack them uh, in the z positive directions. So when you want to model this cohesive surface to hood surface contact, I think you need to choose this one, right? I'm a bit old right now, so I think this one. Yeah, click continue, or let me check again a little bit. uh okay, or maybe tie, not tie equation. No, 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 no. I think it's here. Yeah, it's self contact. I think it's surface to surface contact, and then you click the master surface. Is this guy? This is, I'm choosing the top one, right? Okay, and then click done, and then you also have another surface, which is the guy below here. Done, and then you have surface surface, finite slating, surface to surface, and then no adjustment. Then surface smoothing, no need. Okay, clearance bonding, and then nothing here. I think what you need to do is to create properties, and then we will have this incident contact. I think it's contact. Yeah, and then what you need to do is basically you want to have this normal behavior, so they shouldn't have this, how to say, they cannot penetrate each other. Okay, and then you also have the tangential, in case they can be friction, can have a friction coefficient here, just make 0.3. This is for the case where they have been delaminated, but then we want to make them that they have cohesive behavior. So you have this cohesive behavior here. So This is the one when the one that you want to use, cohesive behavior. So click here. Just choose the default. So they have this cohesive behavior, and then you want to use this fracture criteria, fracture or damage. I think it's not fracture, but it's damage, I think. Yeah. Yeah, this is what you want to do. So the criterion, I recommend you to use the quadratic traction because this is well known to be more effective for a mixed mode. So in this case, I forgot what value did I use. 40. Let's check the notebook. I think I used 40, right? For the initiation. Yeah, 40. No, this is for the hashing. Yeah, I think no, this one is for the cohesive elements. I think it's 40, 60, and 60. And then you want to specify damage evolution. We want to model the energy, and then they will have a mixed mode behavior. They're following VK model, and then the power exponent is 1.2, and then this guy is about, I think, is 0.4, 1.2, and 1.2. Okay, so they're good right now. And then if you want, you can put some stabilization, 0.01. In this case, I use 10 to the minus 3 to make it faster, to make it the simulation faster. But the recommended value for research grade simulation should be 10 to the minus 4. Okay. Okay. And all right, guys, so let's continue again. So this is the contact interactions, master surface, surface to surface. uh where was it? Why I forgot. Yeah, I think I already make this one. Okay, and then now what we need to do, just click OK. So they will have an interaction here. If you want to check the interaction that we use, this is the contact. We have the tangential, we have the normal to make sure that they cannot overlap each other. We have the cohesive behavior between them, and then we have the damage. This is the stabilization, this is the evolution, this is the initiation. Okay. All right, guys, let's continue again. uh yeah, so this is the evolution and everything for the contact behavior. Okay, so we choose for the first one. Now we continue for the next one. We create the same thing. This is the second interaction. Choose the upper part. Oh, click continue first. Choose the upper part for this guy, and then the lower part of this guy. Surface. Done. And then the interactions, the same interaction. Okay, and then continue again. Create again this one. Continue the upper part. Click done. Surface, and you rotate to get this lower part. Click down and then OK. Now they have everything. They have the contact behavior already set. So what we need to do is just to give the load. But before we give the load, let's put them in the correct location by coming back to assembly and do the translate instance. Click this guy, click done. So you zoom here, click here, and then move to here. Okay, click OK. Then repeat again this guy, click done, zoom here, click here, then zoom here, and then click here. Okay, it's pretty simple. Click again here, done, click here, and zoom here until you can get this point, and click here, and then done. So now all the plies are well oriented, and they already been set in terms of the contact behavior, contact cohesive surface contact. And then now you already locate them in a correct position, and then the next thing is to make a loading, and then click here boundary. It's the same, just creating a displacement. Continue. Yeah, you need to. So if you cannot choose the whole face, click here faces, then by face angle maybe. So you cannot do it like this, so you need to choose one by one. So press shift, click, 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 zoom again. Okay, click done. Then give them everything. Okay, did another step? Okay, and then make sure for the loading you choose the step number 1, then click here. Okay, you click continue, you choose the surface, 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 and then click done. And then you click everything except now you give this u1 equals 3, so you pull only 3 millimeters. Oh no, I think it's 7. No, oh no, it's different. Now the total length is 100, right? So if you want to apply 3%, yeah, you put 3. It was correct, yeah. In the previous video, the total length is 200, so you put 7. Okay. Okay, and then we give the load. Now the mesh time. Mesh time is easier. Click part. For part 1, you click and then you put the size 1. The recommended size always 1. And then for part 2, the same thing. You mesh it, size not 1. Click OK, mesh, and then you assign this guy. Please don't forget to use continuum shell. Don't repeat the same mistake. Second order enhance element dilation, specify 0.999 to avoid division by 0. And the viscosity you put 0.01. Okay, click OK, and then make sure that you put the correct stacking direction by clicking this guy, assign stack direction. So you choose this guy. Oops. Okay, yeah, they are already correct now. Okay, then choose the 90. Okay, this is the top, I think, right? Level. Yeah. Okay, so make sure view tools, query, mesh stack orientation. This guy will be brown and this guy will be purple, not this side. Okay, sometimes this side is the purple and this side is the brown. This is wrong, so you need to fix it. Okay, especially when you create a lot of partition here. In this case we don't have partition, so maybe even if you don't do it, it will be correct. But if you have partition, Abaqus messed up. So it's all right now. So what we need to do is just to run create and then job model 2 using a cohesive surface, and parallelization we use 4 to speed up, and then okay, and then click here and then let's run submit. Oh, at least, oh, okay, I already have boundary condition because I used the previous file. So let's delete this because I have this boundary, so I just click here, so they will not be included. Job and submit, and then I hope it's running right now. Let's see, monitor. And yeah, so make sure you check the previous video on how to do the same thing using this cohesive element. Oh god, now, oh surface-based cohesive behavior cannot be used with finite sliding surface-to-surface contact pairs. Okay. So let's come back again to this. It's good that we found this error. So where is it? Interaction. So we need to choose this guy. They cannot do it to finite sliding. Why I can't modify? Oh, this one. I should be able. Small sliding. Node to surface. I think. Click OK. Small sliding. Node to surface. OK. Small sliding. Node to surface. OK. Maybe it will work because that's the only concern that why Abaqus aborted. They said that they cannot use finite sliding, so put small sliding and not the surface. Maybe the algorithm is not prepared for that. So yeah, I don't know why. It's still error. My God, 5,000 element. Oh yeah, I think I didn't use continuum shell. Oh, or maybe here I use a no shell. It's already shell homogeneous, right? Shell homogeneous. Shell homogeneous. Yeah, everything is shell, but how about the mesh? Let's check this guy. It's continuum shell. Yes, it's correct, but maybe the other one I haven't set it. Maybe. Okay, done. Oh yeah, you need to use this guy. Yes, in modulation specifies 0.999, and then for the viscosity you use 10 to the minus 3. Click OK and done. Then you create job and then submit again and then OK. So it's good that in this channel we show what it is happening when you try to run and then you found errors and then we try to debug it. Uh, so you will have the experience of how to deal with the error message. I'm not the kind of guy who wants to hide everything. And then suddenly when you try to do my videos and then you end up saying, oh, it didn't work, Dito. How come? So yeah, it is good that we found errors. But the simulation can take a long time because as I told you in my previous video, my current laptop is not that good. It only has two processor. Yeah, I think it's two processor. It's gonna take some time to run, and then I will pause and see you later. Hi guys, welcome back, and let's continue again. It's not yet finished, huh? But if you see, maybe if you it's not still running, so if you see that there's something strange with the model, that now they are separated like this, so I thought there might be something wrong with the definition. So the default value, maybe it's worse than this. If you click resolve, maybe what you see is not something like this worse than this one, but you need to click here common options. The default value is the auto compute will be like this, so what you see is going to be something like this. Wow, it's strange, right? It seems that between this one and this one they don't have this contact, and you want to fix it. So but this is actually 30 times. We magnify the deformation 33 times, so it's too exaggerated. The actual one is something like this, but still we have this kind of separation, which is I don't think it's correct. So what I want you to do is to check this interaction. You need to go back to the interaction, and then you can check here. If you check the interaction one, it's correct. So uh, so so if we rotate this guy, it seems like it's correct, right? Between this face and this face. If we check interaction 3, it's also correct. But if you check interaction 2, turns out I make a mistake. So turns out that I choose the wrong surface. Look at this. Okay, so my slave surface is wrong. Okay, so what I'm gonna do, I'm going to choose the new slave surface. Okay, So what I'm gonna do is that I'm going to go to assembly, and then I will translate the instance from here. So I want to translate around. So just click 000, click enter, and then put 10. So what I'm gonna do is basically I'm just slide this guy a little bit outside, so I can choose it again later during this interaction. I have tools. The problem, let's check again here. The problematic is that I should choose the lower part, but instead I choose the upper part. So this is surface 3, which is wrong. So you can click here, tools, surface, edit, edit surface slave 3, which should be the lower part instead of the upper part. Then click dismiss, and then you go back again to assembly, slide it back again to the original location, click here, translate, and then you click this guy, click done, and then you click zoom to this point, and then tell him to move to here, and then everything set, and then let's run it again. And then click kill, you kill the current job. It's gonna take some time to kill it because my computer is not good. So just make sure before you click again, make sure this running shows terminated status. Terminated status, okay. Still not yet. So yeah, just to give you idea of how slow my laptop currently is. And gonna take some time, guys. So I think it's better to pause, or maybe not, or yeah. It takes so long just to kill them. Yeah, it's already terminated, but the status still not updated. So dismiss, click open again. So yeah, now it's terminated, so it's good. So now you can submit again, click OK. Because if you just kill the Abaqus CAE, sometimes there is some file that is still active. Oh, still aborted. What is happening? Why? See, there's still some file. I just want to tell you that, and it's happening. So there is this log file that is not deleted yet because we submitted too early. So the computer don't have time to erase it. Then you click submit, and then this happen. So what you need to do usually is complicated. You need to delete this log file, LCK file. Right click and delete, and let's try to run. Hope we are lucky. Otherwise, we need to save and then reopen everything from the beginning. So make sure when you have a slow computer, things are not as easy as expected. So now it's submitted. Hopefully, let's check. Yeah, I think it's good. It's aborted again. Come on. See, there is this problem of parsing and shutting down all the sockets, and yeah. So we are going to pause first the video. Or let's see. That's how I deal with it. So what you need to do is basically just to delete everything except the input file. The Yeah, I think the input file. I think. All right, right click and delete. I'm not sure I can delete everything. I'm not sure. See, there's this ODB file still open. File, close ODB. Everything is closed, right? There's no ODB right now. But yeah, this guy sucks. Try again. Skip, skip. This is the file that caused the problem, guys. Huh? The SMA. So there's still some process working on. Let's check the task manager. Sometimes you need to kill the Abaqus CAE. So it's a really good. In today's video, we learn a lot of things. Where is it? Details or where? Abaqus standard. I hope it shows. Usually it will not show. Oh yeah, here. here standard running, so you need to end this. Okay, and then you can, yeah, and then this guy gone, and then you can resubmit everything. So basically what happened is that when it shows aborted here, the process is not aborted yet, so you need to be patient, especially when you have a very slow computer like mine. Okay, now it's submitted. Hopefully it's working this time. It's running, it says. Let's say, let's see, not let's say. Let's see if it's working. At least give me the first iterations. Okay. All right. So I think it's working right now. So there is no error, still running. Now it's second step. I will show you once it's done. So let's pause first. All right, guys, let's continue the video. So it's still running, and if we see the monitor now, it's almost 40% of the total load that we give, and we can already check the result if you want. And this is the zero. This is zero. There are two plies. There's a 90-degree layer. And if you see here, the damage in the 90 already started around 0.99. So yeah, this is how you model the cohesive damage. No, sorry. This is how you model mesoscale modeling of composite using the cohesive contact behavior. If you want to check the load displacement curve, you can do the same thing. You can click here, ODB field output, continue, and then click unique nodal, and then you click the reaction force. In this case, you want to check the reaction force in the x direction, RF1, and then you click here, you edit, and then you choose the whole. Let me orientate it nicely. So, oh my god, I cannot see anything. Maybe this guy. It's already one. So yeah, so it means that now it's already damaged. Yeah. So I need to choose this node, the node here, add edit, and then choose all of this guy. Node done. 200 nodes, 208 nodes, and then save. Okay, and dismiss. I sure it's 208. Why is all too much? Let's delete again. Okay, let's do it again. uh, Click here, continue, unique nodal RF, and then edit, and then you just choose this guy. Done. Oh yeah, it's 200. Okay, and then dismiss. Oh, it's still saving, and dismiss, and then click here, operate and XY data, and then you sum them, double bracket, and then put this one, click here, and then here, and then shift, and then click, then add to expression, save as. Okay, and then you can plot the expression, and this is the load displacement. So it increased from 0 to -10. Oh, okay, sorry, I need to give the negative here to make it positive. Plot the expression. So yeah, this is the load displacement curve. So start from 0 in increasing, and then start breaking it. Okay, so enough for today, guys. I hope these uh, videos useful for you. If you have anything to ask, please comment below. Don't forget to subscribe. Goodbye.